Ready? I'd like to give the cat, a chance to participate in the lecture, but I'm not sure he wants to. Anyway, welcome to everything you need to know about samples, how to design them, how to do a random sample, all of the things that you need to know. And one of the reasons why this is really important is because you're working with a sample for your research report, so you really do need to know something about the samples. Okay, so the first thing that we're going to do is talk about sample design and the options that you have about the kinds of samples that you can take. And then we're going to talk about the considerations that go into figuring out the size of the sample that you need to take. I think across the board, lots of folks will listen to a poll on the news, or they'll critique something and they'll say, oh, the sample size is too small. You can't draw a generalization from that because the sample size is too small. And like almost uniformly, they're absolutely full of it. Like almost uniformly, they're absolutely full of it. The mode, some of the design choices that you make often matter more. And to be honest, usually the size of sample that folks need to take are a lot smaller, at least to be able to make a top line generalization, like about the support for a political party or a rating of a party leader. Like if that's all you're going to do and generalize from that, the sample that you need to take is usually actually much, much smaller than folk think it is. Okay, so first things first, how do we design a sample? What are the choices that we make when it comes to designing a sample? The first choice that we have to make is between probability sampling design and a non-probability sampling design. This is basically the choice between a random sample and a non-random sample. And so inside each of these buckets, or under each of these umbrellas, there's a whole bunch of random sample choices that I'm going to lay out for you, and I'll cue which ones are the Canadian election study. And then there's a whole bunch of non-probability sample designs that I'll walk you through as well, but I'm going to spend most of my time talking about the random sample designs because these are the ones that we actually use. Okay, so why do we care so much about a random versus a non-random sample? Or why do we care so much about a probability sample versus a non-probability sample? And this cues the numbers that are going to come later on when we're talking about probabilities, right? So a probability sample is a random sample. In a random sample or probability sample, the most important thing you need to know about it is that every single member of the population has a known non-zero probability of being included in the sample. This is what gives random samples their power. Everyone in the population, we know the probability of them being included in the sample, and we know that it's not zero. This lets us use things like inferential statistics, right? In non-probability sampling, or basically non-random samplings, there's just no way for us to know what the probability of somebody's inclusion in the sample is. So we have no assurance that every member of the population at least has some probability of inclusion. And often we know that for a bunch of them, it's going to be zero in a non-probability sample. And so that's why we want to use the probability samples, because everybody's got a known non-zero chance of being included in the sample. There are two big reasons why we like this, in addition to like just that top line thing where like we want everybody to be able to have a chance to be included. The two other big benefits that come from a random sample or from a probability sample, random and probability sample are the same thing. The first thing is that it avoids conscious or unconscious bias. It takes a lot of the choices out of the hands of the researcher, just like randomization in other contexts of the course. We use randomization to mitigate conscious and unconscious bias, which is great. We know that we want to do this, right? The other thing that probability samples give us, or these random samples give us, is that we can use inferential statistics. And so this is like, we need a random sample if we're going to use something like chi-square to generalize from the sample to the population that the sample came from, right? So in order for us to be able to use those statistics, we have to have a random sample. The computer will run anything that you want on a non-random sample, but it's inappropriate and we would not be doing our work well if we used those statistics to generalize from a non-random sample to some kind of population, right? Like we just can't appropriately do that. So this is why we like those random samples. Everybody's got a known non-zero chance of being included. We do that because it minimizes and avoids unconscious and conscious bias, and it opens up inferential statistics for us to use them. Now, if I were to ask about something like this on a test, one of the things that I would do is I'd be like, well, what's the difference between a random and non-random sample, or what's the difference between a probability and a non-probability sample? And like, these are the kinds of things I want to see, like, what's the probability that somebody would be included? Why do we want to use probability samples? Things along those lines. So given that random samples are so useful and like allow us, are required for us to use any kind of statistics, why would we ever use a non-probability sample? Why would we ever use a non-random sample? Like what serious considerations would we have that would lead us to do a non-random sample? The first usually relates to resources. So we would do a cost-benefit analysis that would tell us that the advantages of convenience of having a non-random sample or the cost savings of having a non-random sample, they outweigh the risk of having an unrepresentative sample. For me, one of the reasons where I've done this is when I've only been interested in an experimental effect. And so then I've used something called Mechanical Turk, which are a bunch of folks in the States in a sampling thing with Amazon. And so we wanted to do a large-scale experiment. We want to be able to speak about generalizability across experimental treatments, and we want them to be regular folks, which this group typically is. But it was like, I think, a quarter of the cost to do it that way than if we were to do like a random population sample. Like it was one of those ones where like we just didn't have the money to do it any other kind of way, but we had really good reasons to not need to do it that way because we weren't trying to generalize to the population. We just wanted to talk about what was going on in the experiment, right? So an instance like that is when you would use a non-probability sample if you've got a good reason that's motivated by your research. The second reason why you would use a non-random sample or a non-probability sample is when you don't have a population list. And one of the things that's become really clear as I go through like your options for like a random sample design, like the choices that you can make if you're going to set up a random sample, you need a like list of everybody in the population that you're wanting to study. Or you need a really good proxy or a really good surrogate for it. And in this case, like, honestly, what we used to use was the phone book.
The new phone book's here! The new phone book's here!
For people, like, in a country. Like, we wanted to sample, like, all Canadians. We would actually just get a hold of their, like, landline telephone numbers. Now, I know many of you are much, much younger than I am, which means that you may not even remember having a landline telephone.
Nope.
I know I certainly haven't had a landline since 2008, I think. Yeah, so like over a decade, certainly. My parents have a landline. Actually, even before then, even before I got rid of my landline, literally the only reason why I used it was to talk to my parents on it. But that was when cell phones were really expensive as well. Anyway, so what we used to use was the phone book. And we would be able to mark things to the census, and we could ask a couple of questions about what was going on in somebody's home, like how many people lived with them, the relationships they had with the people who lived with them. And we could get really good markers about the kind of household that it was. We could mark it to the census, and we would be really confident in the reliability of our estimates because we were really confident that if we knew that somebody had a landline telephone and like a couple of other things about their household, we were really confident. Like we were really confident in that proxy population list. Now we don't have that. And so I'll raise it when it comes up to like when we can trust an internet sample and when we can't. But there like was this period here where like without the phone book, we really didn't have a good list of who was in the population. And without that, you can't do a random sample. Or I mean, you can, but they're not very good. I'll explain that in a moment too. And so one of the things I want you thinking about, particularly if you're going to be hard on folks for not taking a random sample, is to ask, well, what's the population list that they would be able to use? And clearly we don't have a list of like everyone in many of the populations that we care about. And so if we've got a proxy, like how confident are we in that proxy? Is it a good proxy? If not, then people might actually have really good reasons for not using a random sample. Okay. So now I'm going to pivot into going through the types of random sampling designs that I want you to know about. There are 5. They are simple random samples, systematic random samples, proportionate stratified random samples, disproportionate stratified random samples, and multistage random cluster samples. I will explain each of these in turn. Okay, the simple random sample is the most basic, and it forms the basis of many other designs to follow. All it is it gives every member of the population an equal probability of inclusion in the sample. So everyone has an equal chance of being included in the study, and every group of people has an equal chance of being included in the study. What this means is that you could have like really weird samples because every individual and every possible group of individuals has an equal likelihood of being included because everybody's just got an equal likelihood of being included. It's the most simple, the most basic. If you've got a small population, you can use the lottery method to be able to figure out your sample. This is really analogous. Do you remember? I don't know if anybody had to read the short story in high school about the lottery, but like, yeah, anyway, this is what you would do. You would draw lots and, yeah, use the lottery method in that section. If you have a larger population, you would use a random number generator to pull your sample. I have done this in a context where I wanted to send out survey invitations to members of parliament. We didn't want to send it out to everyone because we knew we didn't have the resources to do a ton of interviews. So what we did was we did a random sample of 1/3 of the members of parliament. And all we did was we like put them all in a list and gave them a number and then asked a random number generator to give us a random list of 30 numbers. And so that was how we got our members of parliament for that particular study. So random number generators, you can literally Google it, random number generator, and you can see what it looks like on the internet. Okay. The big benefit is that we know that everybody's got the equal probability of inclusion and then all the other benefits that go along with random samples. The drawbacks to random samples are twofold. The first is that it can produce really extreme samples. It's possible to use a simple random sample and get a really extreme result because every possible combination of people has an equal probability of being included. So you could take the sample and only get people with green eyes. That's totally possible. That's equally possible than getting like a distribution of all of the eye colors, things along those lines, right? You could take a sample and only get people who are age 22. As opposed to like getting a nice distribution of like all of the other ages. Like you would actually expect it to be representative, right? So the drawback is that it can get really wacky because that's an equal probability, right? The other disadvantage is that it is tedious and time consuming unless you've got a population list that's electronic or unless you can use computers. Basically, if you cannot use computers, doing a simple random sample is tedious and time consuming at best. Okay, that's random sample type 1. Random sample type 2, this is the systematic random sample. For me, the best way to understand a systematic random sample is that you have a population list. You literally have the list right in front of you. And what you know is the total population, and you also know the size of sample that you want to take. So let's say you've got a list of everybody in a small town that has 10,000 people living in it, and you want to get a sample of 500 people. What you need to do is you divide the population size by your sample size. So 10,000 divided by 500 gets you 20. And this is something called your sampling interval. Sometimes this is marked by K. So your sampling interval is marked by the letter K. What you do is you get your sampling interval, so in this case, the first 20 people, and you randomly pick one of them. Then after that, you pick the 20th person after that, right? So let's say we randomly select one person amongst the first 20. Let's say we get the 14th person, and then after that, you select every 20th person. So it's person 14, person 34, person 54, person 74, until you work your way down the bottom of the list. But the setup is pretty straightforward. Like, you have your list in front of you. You know what your sample size is. You figure out what that interval is, randomly select the starting point within that first interval, and then you just take the interval down after that. Here's the advantage. Once you get it set up, it's actually pretty slick and pretty quick. So it's less cumbersome once you get it set up than a simple random sample. And because of that, you don't have this thing where everybody's got the equal probability of being included. And so what this means is that it reduces the risk of an extreme sample, because you can no longer say that every possible combination of people has an equal likelihood of being included in the sample, right? The big disadvantage, though, is that if you've got a list that's got a cycle to it, or if there's something that structures the order of the list, you're going to get a goofy sample in that context. It's going to put something else into the sample there. Think about it in terms of alphabetical order, right? I was literally the only person with a last name that started with T in my class from kindergarten to grade 12, right? I went to a small school, admittedly, but when it's line up in terms of alphabetical order, there's going to be clusters around some letters, and that usually maps onto things like place of origin, geographically in the world. It can map onto things like language. It can map onto things that matter, that we care about, right? And so that can produce a cycle in the actual sample that we may want to avoid. The other big disadvantage for systematic random samples is that, if the example is you have the population list in front of you, you really can only do it if the population is pretty small, right? Imagine having a list of 34 million Canadians and you're going to do a systematic random sample with it. We would not do this, right? So you need a small population plus a really good list to be able to do that. Okay, so simple random sample is sampling type 1 of 5. Systematic random samples, the one we just did, is type 2 of 5. Type 3 of 5. This is something called a proportionate stratified random sample. So what we're doing here is we're using a design to ensure that key groups within the population are represented in their correct proportion. And the reason why we do this is it provides a good solution to the problem of extreme samples. And so what we're doing with a proportionate stratified random sample is that we know something about our population. So we'll know that it's got a certain age profile. We'll know that it'll have using Canada as an example, we'll know the distribution of Canadians in terms of age from the census, and we'll have a pretty good idea of what province they live in, again, from the census. And so if we're going to be taking a sample of Canadians, two of the things that we do a proportionate stratified random sample on is how old they are and where they live. And so what we'll do is we'll divide the population into groups based on those things that we're stratifying on. We call them strata. Like stata, but with an R, you could just call them groups. Of course, the cat is choosing right now to munch on some kibble. Thanks, Winston. That's great. Anyway, okay, so you've got strata, like stata, but with an R. This is just your group, your province that people live in, or their age group or something along those lines. And so what you do is you divide the population into groups based on, these characteristics that you care about. Then you select a sample from within each group, and then you combine the samples together to get your representative sample. The reason why we like to do this, well, and I should say, the stratification variables, the things that we divide into groups, they need to be two things. They need to be relevant to our research question, like relevant to the stuff that we want to explain. And they need to be things that we can actually operationalize. So if you remember back to like operationalization back at the beginning of the course, yeah, we need to be able to operationalize our like stratification variables when we're actually using this particular technique for generating a sample. And they also need to be relevant. So this is one of those reasons why like age and where you live matter. So particularly if you're studying this for an election or for public opinion, like we think that region matters for things like vote choice. We can see it. So yeah, like it seems reasonable to think that it matters. And we know that like how old someone is also affects how they think about these things. And we know we have really good like ways to operationalize both of those things. And so this is one of the reasons why like age and province that you live in, they make sense in this context. The two big advantages of a proportionate stratified random sample are as follows. First, it avoids extreme samples for the characteristics that you're using to stratify. So for the characteristics that you're using to divide the population into groups. And so to use our examples of like age and the province that you live in, we're going to be taking a random sample within age groups and within provinces, say, and we still have the possibility of having an extreme sample inside each one of these groups, but it's like contained into that particular group. And so it minimizes the risk overall, which is good. The second advantage is related to this. Either we can keep the same sample size and increase our accuracy because we know that we've like reduced the risk of an extreme sample. So we keep the same sample size and we can achieve a higher level of accuracy, or we can keep the level of accuracy constant, but take a smaller sample. And usually, sometimes it's cost and resources that really drive us to take a smaller sample. And so if you know that you're like tight on resources, one of the things you're going to do is stratify on things that you know are relevant to your project, because you can achieve the same accuracy with a smaller sample, which means that you can achieve the same accuracy at a lower cost. So proportionate stratified random samples minimize sampling error because we're like making these homogeneous groups that we just take proportionate samples from. Okay. The big disadvantages for the proportionate stratified random sample. As you can imagine, depending on how I'm defining like age and province or which age groups I'm using, it can, like the groups that I'm sampling in proliferate really quickly. You can only stratify on a few things. You can only divide your sample that you're going to take into like homogeneous groups so many times. Otherwise, it just becomes a mess. It just becomes very difficult to do. The other big disadvantage is that you might have a theoretically crucial variable that you want to stratify on, but if you don't know what the population value is on that ahead of time, you can't stratify on it. So you need to have a certain amount of knowledge of the population before you go in to doing a proportionate stratified random sample. Because if you don't, then like you actually just can't do the method. You wouldn't know how to divide the groups in their like proportions that are actually in the population. Like if you just don't have that knowledge of the population, you just can't do this particular way of doing it. Okay, so that was the third option, proportionate stratified random sample. Option number 4 is disproportionate stratified random samples. It's the exact same thing as the proportionate stratified random sample, but instead of like keeping every strata or every group in their population proportion, what you do is you oversample one of them. So you deliberately oversample some groups, or you could deliberately undersample others. There's a couple of reasons why we do this. This helps facilitate our statistical analysis if we can kind of equalize the distribution of characteristics that we think might be important for causing the thing that we want to explain. So some of you have already run into this in your research reports where you've got a distribution that's skewed and you've got a really small number of people in a category that you actually really care about. And so what you could do is a disproportionate stratified random sample, in theory, and what you would do is you would oversample on the stuff that you cared about because you knew that it was something that you were interested in, right? The other way, or the other big advantage, is that it ensures that we have sufficient cases for meaningful analysis when one group is small but really important, either in terms of substance or in terms of theory. So this is the thing. The Canadian election study is a disproportionate stratified random sample. They do a disproportionate stratification on province and on age. For province, where they do the disproportionate stratification is with Quebec, because Quebec has a very different set of factors that go into vote choice. So what that means is that they need to have a large enough sample from Quebec to be able to do standalone analyses for Quebec. And it's like, you can see it. You can see the reason why. Like plain as day, it's because they've got different political parties that compete. And so this is why you have to do a disproportionate stratified sample to make sure that you've got enough people from Quebec to be able to do any kind of meaningful analysis. The other way that they stratify disproportionately is on age, and it's because Elections Canada partners with the Canadian Election Study, and for quite some time they've wanted to know what was going on with youth voter turnout, so folks in the 18 to 24 age bucket. And in order for us to be able to do meaningful analysis to figure out what's going on there, we would need to oversample 18 to 24-year-olds. Through this work, one of the things that we found is that 18 to 24-year-olds in post-secondary, particularly in university, vote at comparable rates to older folks. So this idea that all young people don't vote, particularly if you've got relatives that are finger wagging at you for being young and therefore not engaged enough in politics or whatevs, you could point to them as a university student and say, well, actually, the Canadian Election Study has shown for a number of years doing the analysis of a disproportionate stratified random sample of 18 to 24-year-olds that people like me with my profile actually participate just as much as you, relative who's being mean to me, who also happens to be older. Ha.
Take that, Mom! Take that, Dad!
If for nothing else, I want to give students some ammunition for gotcha moments, depending on if that's how your family operates or not. Anyway, I say optimistically, thinking that we'll be able to gather with our families anytime soon. Yeah. All this to say, it's the disproportionate stratified random sample that shows that a lot of the lower level youth turnout, particularly in Canada, is driven by folks that graduate high school and then exit the education system entirely. They're really hard to find and target in terms of election administration, advertising, and things along those lines. Okay. So that's the disproportionate stratified random sample. That is the Canadian Election Study. So it would have similar drawbacks as the proportionate stratified random sample. We would just do the proportionate stratified random sample, but then kick it up a notch for groups that we cared about. Last random sample design that's available to you. It's something called multistage cluster sampling. When would we use this? We would use it when there's no population list available. So what you do is you do a random selection of clusters of population members, and then from within each cluster, you do another random sample. So for me, instead of trying to explain this in a hypothetical, you can just come up with 3 clusters and then sample within each of the clusters. Here's another way to think about it. We know that Canada's got a set number of electoral districts. Federally and provincially, but we'll just use federally as an example here. So we know that Canada's got 338 seats. I think that's the map that we ran on in 2019. So 338 seats in the House of Commons. They each come from a geographical place. That's an electoral district. We know we have a list of 338 of them. Say we want to sample voters, eligible voters, but we don't have a list of them, or Elections Canada won't give us the list. So what do? We can draw a random sample of electoral districts. Within each electoral district, we can draw a random sample of something called polling divisions. And all a polling division is where you physically go to cast your ballot. So if you ever voted in person, This would be like the school gymnasium or the community center or whatever, where like you actually have to physically show up with your card to like get your ballot and vote. Yeah, that's your poll division, basically. So we know that we have districts, we know that we have poll divisions, but what we want to get out of the eligible voters. And so what we can do is like randomly sample. If we're doing a multi-stage random cluster sample, you could randomly sample electoral districts. You could randomly sample poll divisions, and then you could from that like randomly sample people who like live in them or something along those lines, right? The big advantage of the multi-stage random cluster sample design is that it eliminates the need to have a population list. Yeah, that's basically the big reason that we would use it. The big disadvantage is that it increases the risk of sampling error. Because each stage has an associated risk of sampling error. And so sampling error is going to be like this idea that you're going to get like a wacky sample where like the sample that gets drawn is not representative of the population, even though it's randomly selected, right? Usually random samples like don't do this, but as we talked about with like a simple random sample, you've got like every possible combination of people is like equally plausible. Or possible under a random sample. And so the more times you increase the chance that you're doing that, the more you increase your sampling error. I mean, we can use this multi-stage random cluster sample if like folks are like far flung geographically or things along those lines. But still, like you would need to massively increase your sample size to get some accuracy with a multi-stage random cluster sample, or you would have to try to reduce the variability by adding like stratification to it or something that just makes it super complicated. So what this means is that you've got these 5 types of random samples. The simple random sample, the systematic random sample, the proportionate stratified random sample, the disproportionate stratified random sample, and then the multi-stage random cluster sample. Of these, the one that's going to have the most sampling error, so like the biggest mismatch between like what the population actually is and what you see in your sample, is going to be the multi-stage random cluster sample. And it's just because you're taking a whole bunch of random samples together at the same time. The one that's going to have the least sampling error is the proportionate stratified random sample, precisely because you're dividing your population into proportionate, homogeneous, or more homogeneous groups. And as a result, because you're doing that division before you take the sample, you're actually minimizing the potential for error because you know that you're getting things, at least some things, in their actual population proportion. Okay, so this is why we stratify when we can swing it if we've got the information that we need to be able to do that. Okay, so then what are these non-random sample designs? What's a non-probability sampling design? There are 3 basic ones that we use. And I'm going to present them from like the least desirable to the most desirable. So the least desirable is a convenience sample. The middling option is a purposive sample. And then the most desirable is a quota sample. So convenience sampling. If you've ever taken a psych class and then been given a study, you have been part of a convenience sample. A convenience sample is just when the researcher happens to select who's conveniently available to participate in their study. So like the first 100 people who agree to be interviewed, students in a classroom, most internet samples, especially if you've got like a really junk commercial polling firm. Yeah. A Twitter poll is a convenience sample, right? They're easy, they're inexpensive, and they are likely to yield a massively unrepresentative sample. Totally. If you're saying they're being like, why are they picking on my psych professors? Don't they do good research? It's like, yeah, but they're doing an experiment. So they actually don't care about generalizability. They care about the experimental treatment effect.
How convenient.
Yeah. So in that context, and convenience samples, okay. It's just that you can't generalize to any population from it, not with any degree of confidence like you would, like you could if you were using inferential statistics, say. Okay. Next best is this thing called purposive sampling. And this is where the researcher uses their judgment and knowledge of the target population to select a sample. So they are purposefully trying to obtain a sample that appears representative. So the probability of being included in the sample depends entirely on the judgment of the researcher. So this sounds super subjective, and you can see that the problems might be associated with this. But in the past, when it's been used, it has been known to yield some surprisingly accurate sample estimates. And if you think about it, like this is what you would have to do as a researcher if you couldn't take a random sample, but you still knew the kind of stratification that you might want to do, right? And so in this sense, like somebody's knowledge of like the population that they want to study actually has some power in this particular context. The best form of a non-random sample that we use though is a quota sample. So quota sampling is the most sophisticated method of drawing a non-probability sample. And the goal is to simply fill a series of quotas so that your sample represents a microcosm of your population. And so this is what you'll often see better internet samples doing. So what they'll do is they'll want to get a set of quotas of individuals specified by certain attributes, like their age, where they live, what their gender is, what their level of education is, and there's going to be a certain kind of combination of characteristics that you're going to want to use as your quotas. And so individuals displaying like the combinations of characteristics that match the quotas are like included in their proportion of the share of the population. So you get to decide the quotas that you want to fill in advance, and then you just like go and fill them, basically. This is honestly what most reputable internet polling or polling firms that use internet samples and do them well, many of them are doing this. Some of them are doing a bit better than this, but like almost all of them are going to like use this idea of quotas. The limitations of a quota sample are that you need like accurate and up-to-date information about the population that you're studying. There's ample opportunity for bias. The only constraint is that like a firm fills their quotas. That's it. And then like stratification, the number of quotas that you can take into account needs to be pretty limited. Otherwise it gets super unwieldy super quickly. So the thing I want to end on is to give you some information about like how we actually go about like building a sample now compared to the past. Like, because remember how I was talking about how like our best like population list used to be the phone book, and now we don't have the phone book. And you're like, well, like where's the list that you're going to get of like any population if you want to be able to like generalize to a whole population, right? What the most common practice is now is that you'll have commercial firms that you'll hire, and I do this all of the time. So what we do is we go to various commercial firms and tell them the kind of project that we're working on, and then we ask them a bunch of questions about the people who have agreed to be contacted by the survey firm to participate in studies. And what we're looking for is to see whether or not the participant pool, like the people who have agreed to participate in a study with a particular firm, for whatever incentives that they're offering and things, like we're looking to see just like how likely it is that the batch of people who are in the pool match the target population. So for us in a study that I ran this term, this is the idea of we're asking firms if they can get us a pool that they can randomly sample, but that the pool is like close enough to Canadians that we can say that we can generalize from our random sample of these participants to Canadians in general. What we can formally technically only do is like generalize from the participants in our sample to the participant in that firm's pool. And this is understood. Like we'll talk about how it's just kind of like we took a representative sample of Canadians from this particular firm. And when we're putting that in our data and methods section, this is cueing to our colleagues who like know the firms whether or not they should trust whether or not we can do the big generalization from our sample to the population based on what we know about how good the participant pool is for any particular firm, right? Some options are anybody who's done a vote compass with the CBC. So the commercial firm that pairs with the CBC for something like Vote Compass, people have the option of opting into like doing more surveys for this firm. And so I know I've used those when I wanted a big like regional sample, like immediately following an election, because I knew that like they would have people in the pool where other firms wouldn't be able to get me a big enough sample. based on that. And this is one of the big constraints that people will have now, is that like a commercial firm might not be able to give you a big enough sample because they wouldn't be able to like draw it from their pool. So like one firm, they were like, we can get you a sample of up to 10,000. And I was like, which is great, but it's 10,000 Canadians. If I wanted like 10,000 people just in Alberta, say, they wouldn't be able to do it. Yeah. Anyway, so this is where we're at now. I'm much less skeptical of like some firms and their internet-based samples because I know that they're doing a good job building their participant pool. Other firms, like whenever I just see them, I'm just like, no. I'll be like, new poll from Main Street Research is usually the top one. But there's any number of others where it's just like new poll by like firm that only comes out with like free public polls and no academic ever hires them. Every time I see like new poll by so-and-so says, and it's just like, I just don't even bother reading the news report because it's junk, guaranteed to be junk. Absolutely guaranteed to be junk. Don't listen to a Main Street poll. That's basically what this boils down to. But like other firms, Angus Reid, Leger, things along those lines, they tend to do better. Okay, that's it for sampling design. Thank you for sticking with me on that one. We've got all of the random sampling designs, the 5 that are a slog, and we've got the 3 non-random sampling designs. Yeah. The last thing we need to do does involve a bit of math. We're bringing back the Z-scores, but you do need to know this to understand like just how big of a sample you need to take to be able to do generalizing, especially generalizing from a sample back to the population. And it's not nearly as big as what you think. Like people get this wrong all of the time. So this is my pitch to stick around for the next video because like it's everything that you need to know about sample size, and guaranteed most people are full of it on this one. So this is what you need to know coming up next.